just before I start, this is joint work with Brandt from Stanford, Nicole Immorlica from Northwestern, and Bobby Kleinberg from Cornell. So residential segregation has been studied for a long time in the social sciences. So just an illustration of what the problem is, here's a map of New York City. So our current location is currently marked, the New Yorker Hotel. So you'll notice if you look carefully that it's actually relatively well mixed in that you have people of all types of races there. However, if you take a look at other parts of Manhattan, for example, South Manhattan is predominantly Asian. North Manhattan, they've got areas like Harlem and Spanish Harlem, which are predominantly black or Hispanic. So the question we want to address here is, why are these areas segregated rather than integrated? And so our goal is to mathematically model and understand residential segregation. And a summary of our results is that in a one-dimensional network with local neighborhoods, segregation exhibits only local effects. So we studied a model introduced in 1969 by Nobel Prize-winning economist Thomas Schelling. So this model is interesting to us for two primary reasons. First of all, up until this point, residential segregation was a policy issue in the social sciences, and Schelling transformed it into a mathematical problem. The second reason we find it interesting is because it's a benchmark model to examine a certain relationship, and that relationship is the effect of local dynamics upon global conclusions. So this is a big area of study nowadays in game theory and economics and other related fields. So I'm going to describe the model to you now. We start with a ring of length n, and each position of this ring at the beginning is either green or blue with equal probability. So then we define what it means for an individual to be happy versus unhappy. An individual is said to be happy if at least 50% of his nearby neighbors are the same color as him. And you might be wondering, how do we define a near neighbor? Well, we have a parameter called W, which is the window size. And we say that an individual's neighborhood is all other individuals within a range of W units or less, including himself. So just to illustrate that, this individual, the blue individual here indicated by the arrow, his neighborhood is this set of 5 individuals if we let W equal 2. So you'll notice that he's actually a minority in this neighborhood because there's 3 green individuals and only 2 blues. In fact, all of the marked individuals here are unhappy. So the question is now, what do unhappy individuals do? And so at each time step, we swap the location of 2 unhappy individuals of opposite colors. So this unhappy blue and unhappy green will swap. So the final thing is, we're studying the process of segregation. So how exactly do we measure segregation here? And the answer is by looking at run lengths. So we're going to look at the run length in the stable configuration. We define a stable configuration to be a configuration in which we cannot find a pair of individuals who would both be willing to swap. It isn't immediately clear that this will always happen, but I'll justify a bit later that we will eventually reach a stable configuration. So for instance, in this configuration here, we have run lengths of 4, 3, 2, and 3. So you can consider the most segregated case to be when if it were all completely blue on one side and green on the other, which would have run length. Whereas a less segregated case would be when the run lengths are shorter. So sort of intuitively, segregation corresponds to longer run lengths and integration is shorter run lengths. So of course, being the first one to introduce this, Schelling did a bit of a few experimental results, and his conclusion, local dynamics will lead to segregation. He ran it on a relatively small case with n equals 70 and a window size of W equals 4. Now, he observed that even though run length of 5 of alternating types would make everyone happy, he observed a much longer average. So we ran it with n equals 1,000 and W equals 10, and we found qualitatively similar results, that the run lengths there are much longer than they need to be. So this process hasn't been studied because it's proven to be very difficult. One of the first results First of all, so the questions here, is run length a function of n or not? So if it's a function of n, that means no matter what the window size is, segregation will be global, and that's unavoidable. If it's independent of n, that means only only an individual's preference will dictate how strong segregation is. So it's kind of a question of global segregation if it's a function of n, and local segregation if it's independent of n. And furthermore, W only and independent of n, is it going to be polynomial, meaning only small local segregation, or is it going to be exponential, meaning more severe segregation? So there's been a few different analyses. The most important analysis has been by Young up to this point, in which he examined a perturbed Schelling model. In this perturbed Schelling model, individuals would make swaps which actually decrease their utility with some epsilon tending to 0 probability. He defined a set of stochastically stable states, and under his definition, he found that the stochastically stable states were precisely equal to the ones which were completely segregated. That is, all green individuals on one side and all blue individuals on the other side. So this is both global because it's dependent on n, particularly it's n over 2, and severe because you can't really get much worse than that. So on the other hand, our result examines the unperturbed Schelling model. In this model, we found that segregation is local and modest. Local in that it's independent of n and only on W, and also that it's modest in that rather than being an exponential function of W, it's only polynomial in W. So we're going to work our way up to this result. The first thing we're going to do is, I promised you that we're going to show that it actually reaches a state with high probability. So the most useful tool in our analysis throughout has been the idea of a firewall. Firewall is a sequence of W plus 1 consecutive individuals, all of the same type. And if you think about it, this is actually a stable configuration. The reason is, consider any individual. His neighborhood is of size 2W plus 1. Of course, if he's in a firewall, he has at least W plus 1 individuals in him. And therefore, it's a majority, and he'll be happy. So first thing we're going to show is that the process will reach a stable configuration with probability converging to 1. And the proof sketch is basically, first of all, with high probability, there's likely to be a firewall in the initial configuration. And you can basically see that by thinking of the initial coloring as a sequence of coin flips. So if it's a heads, there'd be a blue. If it's the tails, then there's going to be a green. So the probability of a firewall of either color being there is the probability that we have at least W plus 1 coin flips in a row of all of the same type. So as the number of coin flips grows without bound, then eventually get at least one firewall with high probability. And after this point, we can see that individuals will have a positive probability of joining a firewall, but then they can never leave. So as the process continues, eventually we'd expect everyone to join a firewall. So that's the first step. We know it halts now. Next, we want to show that segregation is local and not global, in that it's independent of n. So we do this by examining solely the initial configuration, actually. So we show the average run length is going to be big O of 2 to the W. So consider a random site and look in one direction until you get to a blue firewall. The question is, how many sites will you have to look before you see a blue firewall? Well, this is equivalent to the question, how many coin flips will you have to do before you see W plus 1 heads in a row? And the answer is big O of 2 to the W. Similarly, if you look the other direction, you'll find a blue firewall in big O of 2 to the W steps also. So if you have blue firewalls on either side, that means a green firewall containing that location can't grow bigger than that length. And that bounds the length of a green firewall at that location. Symmetrically, you can say the same for a blue firewall, and therefore the average run length is going to be big O of 2 to the W, just using the initial configuration. So up to now, we've shown that segregation is not global, it's in fact local. But the question still remains. I showed a big O of 2 to the W bound. That seems pretty bad still, but we're going to show now that the average run length is modest, in that it's polynomial in W. This proves to be a bit more difficult. So one of the techniques we're going to use, we're going to define something called a firewall incubator, which is basically rich compared to the other. We're going to show that these happen fairly often, and then we're going to show with a reasonable probability that they're going to become a firewall. So just to give you some intuition behind what exactly a firewall incubator is, well, I'll show you a few of our simulation results. So we have a initial configuration of the ring. And the graph above it represents the concentration of how strong we have blue individuals versus red individuals at a location. So the blue and red lines there indicate a concentration of at least square root of W individuals of more, sort of, it's unbalanced in terms of square root of W and more individuals of one type than the other. So you can think of that as being one standard deviation away from the mean of what you'd expect. So as the process continues, you notice that the peaks become more and more pronounced, as do the valleys, until we eventually reach a final configuration here. However, if you follow it backwards and pay attention to where the peaks and the valleys are, you'll note that these firewalls originated from places it was already one standard deviation in the mean. So the intuition is that those areas which are already heavily concentrated in one area are firewall incubators, and they will eventually become firewalls. So there's going to be four squared, and the first is that firewall incubators are common. Now, before I formally define what it is, we require something called bias, representing. So if you map each blue individual to a +1 and a green individual to a -1, then you can add up all the signs within one neighborhood to get a value, and that value is a bias. For example, here we have four blue individuals, which adds a +4, and a green individual, which is a -1. Therefore, the bias of the location between in the middle there is +3. So a firewall is going to be a configuration of 3 blocks. We're going to have a left defender, an internal block, and a right defender. Notice that there's also things called left attackers and right attackers. Those are not part of the incubator. They're going to be used in the dynamics of the process, which we're going to talk about a bit later. So the basic idea is that the firewall incubator is at least 2W plus 2 sites where the bias of every site is at least square root of W, either positively or negatively. There's one more condition which I've left off here, but basically for analysis purposes, we're going to require that the minimum bias of the left defender is at its left endpoint, and similar for the right defender. That helps the analysis a bit later, which we'll show. So the first thing to show is that firewall incubators are relatively common, in that for any 6W consecutive sites, we have a constant probability that it contains a firewall incubator in the initial configuration. And the proof basically follows using the central limit theorem and random walks. In particular, a useful tool in the analysis of random walks called the reflection principle. So after that, we want to define an event in which an incubator deterministically becomes a firewall. And so we're going to take a closer look at the dynamics between a defender and attacker. A defender, you can imagine, we want it to become a firewall. So at the beginning, there's going to be some green individuals in this blue defender. So if we want it to become closer, it would be a good thing if he moved away. So a good swap is going to be when a green defender moves away, like such. On the other hand, we want the blue individuals and the attacker to stay there because they help us out. They make everyone in the defender happy. So a bad swap is when a blue attacker moves away. And so we're going to sort of formalize this and actually say it in a way that helps us. So we're going to define something called a transcript. Again, as before, we map a blue individual, this time only the ones in the attacker, to a +1, and the green individuals in the defender to a -1. And we list their signs in the reverse order that they swap. So that if the partial sums of a transcript are all non-negative, then the incubator will become a firewall. To give some intuition behind why this is, consider any prefix of the transcript. It basically tells us how many individuals are left at a given time. If it's positive, that means there's more blue individuals than green individuals. That means everyone in the defender remains, all the blue individuals in the defender remain happy, and the process can continue. If this is true for all prefixes, then eventually there will be no green individuals left in the defender, and we will have another firewall. So that's the event we want to happen. And now we're going to show that, assuming the swap order is random, that this event will actually happen. We do this using the Ballot theorem. Ballot theorem says with probability A minus D over A plus D, all the partial sums of a permutation of A plus 1s and D minus 1s will be positive. So you can think of this as if there were an election and you have A votes for the winner and D votes for the loser, and if you pick them out one by one and count each winning vote as a +1, then he'll basically be always in the lead. So in this application of Ballard's theorem, we're going to let A be the number of blue attackers and D be the number of green defenders. So based on the definition of our firewall incubator, we're going to have that A minus D is at least theta of W to the 0.5. And this is because we said that each location is biased with at least square root of W. On the other hand, we're going to have also that A plus D is less than or equal to 2W plus 1 actually, because that's the combined length of the attacker and defender. So having these bounds on the number of good swaps and bad swaps lets us actually say that each defender will survive all the way till the end with probability 1 over square root of W. And if this is true for both of the defender configurations, then we actually make a firewall. So we have that an incubator becomes a firewall with probability omega of 1 over W. So there's one thing we assumed here, order is random. And now I'm going to justify that the swap order is close to random. And why do we want the swap order? Well, the swap order is going to be close to random, and it's going to be that's going to be true if the number of unhappy greens is equal to the number of unhappy blues. To give you some intuition behind why this is, consider if there were only one unhappy green and many unhappy blues. If that were true, then the unhappy green is guaranteed to participate in a swap. On the other hand, you only have 1 over the number of unhappy blues of each individual actually participating in that swap. So that would not be an equal chance of a blue, any given individual swapping. So we show that the number of unhappies of each color is relatively close using something called Wormald's theorem, which basically gives us a way of approximating a discrete time stochastic process using the solution of a continuous time differential equation. So this was technically non-trivial due to issues with an infinite number of differential equations. As you can imagine, as n grows very large, we'll have more and more differential equations, and it's not clear what's going to happen there. It in fact causes issues with Wormald's theorem. So we managed to get around this using some clever analysis techniques. In fact, we didn't need to solve the differential equation here. We only exploited some of the symmetric natures of the problem. For example, you know that if you swap x's and o's, then everything will be the same. So we exploit that symmetry in order to show what we wanted to show here. So putting everything together, we have that firewall incubators occur every O of W locations, that each one is going to become a firewall itself with probability proportional to 1 over W at least. And then putting those together, we get that firewalls occur every O of W squared locations. Going back to a slide from earlier, now we can say something stronger than before. So now, again, pick a random site and look one direction until you find a blue firewall. Again, this time it's O of W squared. Similar for the other side, and therefore the length of any green firewall containing that location is upper bounded by O of W squared. And the symmetric thing can be said for a blue firewall at that location. So that gives us what we want, that the average run length in this final state is going to be big O of W squared. So in summary, this is we've provided the first rigorous analysis of Schelling's segregation model on a one-dimensional ring. And we demonstrated that local modest segregation occurs, which by local we mean that it's independent of n, and modest we mean that it's polynomial in W. So in this talk we've shown W squared. In subsequent work we've managed to narrow this gap and actually show the tight bound of theta W. We originally listed this as an open problem in the version of the paper, but we've since resolved this issue. So of course, there's a few open problems we'd still like to investigate. One thing we'd like to do is vary some of the parameters. For example, the proportion of each type of individual. We started with half and half. What if there were, say, 3/4 and 1/4? Also, we could vary the number of types. We considered only green and blue individuals. What if we added more than just 2? Finally, you can picture different tolerant individuals, like perhaps more or less tolerant individuals. Finally, we'd like to study segregation on other graphs. For example, Schelling proposed also a 2D grid model. This shows a simulation result of a 2D grid, and you can see that it provides interesting looking results. First of all, it's unclear, how to actually define segregation in this model because it looks so different from what we've looked at so far. But on the other hand, it seems non-trivial to extend our current techniques to this model. So that concludes my talk. Thank you.
Questions? If the swapping is worst case instead of a stochastic model, do you know what happens? Like, does it always converge, or do things become bigger or smaller?
So if it's worst case, we have actually observed cases in which you can have cycling. For example, like there's fairly small cases where you could consider a few swaps will give you back the exact same configuration and it could cycle forever. But of course, these happen with very low probability as time continues.
Yeah.
Sorry, can you repeat that? How many? How many pairs swap all at once?
How do you define the run length?
Oh, so we define the run length as the number of consecutive individuals of the same color. So, for example, if we had 4 greens in a row.
The time that it takes to run. So how many steps that it takes to run? How do you define how many steps it takes to run and complete it?
The entire process?
Yeah. Because you're saying it doesn't depend on n, but that is ambiguous.
By the run length in that case, we meant that the run length as in the ring configuration, not the running time for actually doing the simulation. Yeah, I believe in that case, if it's a function of n, then we actually do get more severe segregation. I don't think we haven't actually, that's what my intuition suggests, and I think that's what our simulation showed earlier, but we haven't actually ran it, or we haven't proven anything on that case.
Why is it that when you mentioned this other result by Young, why is it that when you add a little bit of noise, then it becomes more segregated?
That's actually a very interesting question, since intuition suggests that would actually even make it less segregated. When you think about it, if they're willing to participate in utility decreasing swaps, that means they're actually willing to become more integrated rather than just staying apart. So that's a very interesting question, and it's something that I think if we could get a cool answer to that, that would be awesome.
No more questions? Let's thank Gautam again.